everyone and welcome back to my channel Be Yourself. This is Dr. Rajni, and in the series of enzymology I will be discussing about the enzyme inhibition. So there are so many things which may inhibit the rate of the reaction. So inhibition can be also affecting directly to the cofactor, not directly to the active site of the enzyme. But here I am discussing only about those inhibitors which will directly influence the active site of the enzyme. So we can say that inhibitor can be anything which can deteriorate the rate of the reaction. So on this basis it can be of two types. So again I am repeating that I will just focus on those inhibitors which are directly focusing or making some changes in the active site of the enzyme, because there may be some other factors also which may inhibit the enzyme rate. So after this we will also be discussing about the kinetics, how this inhibitor will influence the kinetics. So it will be not the same way of kinetics as in the presence of another inhibitor which are not influencing the active site. So inhibitor can be of two types, reversible and irreversible. So here first I will be discussing about the reversible inhibition. Reversible inhibition is basically of four types, which is a competitive inhibition, uncompetitive inhibition, non-competitive inhibition and mixed inhibition. In this section we will particularly focus on the competitive inhibition and also the kinetics, how this competitive inhibition will influence the kinetics of the reaction. So let's start. So competitive inhibition. Suppose here we have a substrate and inhibitor. So we can see here that substrate is complete or star shaped, whereas some of the portions are missing in the inhibitors. This is just an example to clarify what exactly the competitive inhibition is. The thing is that both the substrate and inhibitors has the tendency to bind with the same site. So substrate where it should bind will be the same site for the inhibitor also to bind. That's why it is known as competitive inhibitor. So how it will influence? When there is a lower concentration of the inhibitor, then it will not influence the reaction rate. But when the amount of inhibitors will keep on increasing, and then what will happen, it will compete with the substrate which is already present in the reaction reactant, and this will eliminate the substrate from its active site to bind. So what will be the result of this? Instead of forming a product of E plus P product, this product will not be formed in presence of inhibitors. Another thing is that here the competitive inhibitor is directly influencing the active site. So either it directly bind to the active site, or some inhibitors may also compete by binding to another site of the enzyme, and this will cause some allosteric changes in the structure of the enzyme so that it will inhibit the binding of substrate to itself. So both of these are categorized under the competitive inhibitors. Now moving toward the kinetics of the inhibitors. So let's start with the reaction. So how we have earlier represented the reaction rate. So we have seen that in the previously, when there was no inhibitor was there, that enzyme was combining with the substrate with the reaction rate K1, and the reverse reaction was K minus 1, and we were having the reaction ES, and when this ES break down into product, it will be giving E plus P. But what will happen when inhibitor will be there? In presence of inhibitor, instead of binding with the S or the substrate, E will bind with the enzyme. So in presence of inhibitor, what will happen? E plus I will be formed, or instead of forming the product ES, EI product will be formed, and in absence of inhibitor, this particular reaction will carry on. Now what happens? Here, as we have represented K1, K minus 1 for the reaction constant for this reaction in absence of inhibitor. So similarly, just like that, in presence of inhibitor, let us represent Ki as the reaction constant when the inhibitor is present. So we can represent Ki as, just like K1, I can represent E into I by EI. or simply we can say product by reactant. So this is question number 1. This will be used in further our analysis. Now second thing is that instead of or previously when we have derived about the Briggs-Haldane equation, what we have seen that the enzyme total or the total enzyme was what was the unbound enzyme plus ES, or the enzyme which was total enzyme was what free enzyme plus the enzyme which has bonded with the substrate. But in presence of inhibitor, we will take one more species of the enzyme which will be bonded with the inhibitor. So this time only these changes will be there. Similar to the derivation which we have seen in the Briggs-Haldane equation, we will calculate for the ES species. So before that we will proceed in the same way. But here we have one species of the enzyme EI, so we can replace this EI with the equation 1. So or we can say that EI, as per this equation 1, we can say EI will be E into I by Ki. Okay, so let's replace this EI value here in this equation number 2. So it will become E naught equals to E plus ES plus, instead of EI I will be writing this one. So E into I by Ki. Okay. Now in this equation what we can see, this species E is common. So let us take it out of the bracket and we will take it E common in both the factors. So I will take 1 plus I by Ki plus ES will be here. Now further we can further simplify this equation as E equals to E naught minus ES by 1 plus I, which is the inhibitor, by Ki, which is the dissociation constant for inhibitor in presence of inhibitor. Now if we will remember the Briggs-Haldane equation, what we were having the equation Km equals to E into S divided by ES. So from here, instead of when inhibitor is there, instead of putting the value which we have used in the case of Briggs-Haldane equation, what we will take the value of E, we will take the value of E of this one. So let us replace this Km with the value of E. So what we will be having, Km equals to E naught minus ES whole will be multiplied by substrate by ES. Now what I said that just like the calculation of the velocity, in case of Briggs-Haldane equation we have focused on the value of ES. So here again we got this in the term of ES. Sorry, one thing I forgotten to put this one. So this will be 1 plus I by Ki. So in order to find out the value of ES, what I will do, I will take this 1 plus I by K to this side, I will take to this side, and further I will express this in terms of ES. So I am taking the next page. So what was the value we are having? We were having Km, and while as we have seen that I will transfer this value toward the Km, so it will be 1 plus I by Ki, and in this side we were having E naught in minus ES. So let's E naught total enzyme minus ES, or the enzyme which is bonded with the substrate, multiplied the whole species multiplied by substrate S and expressed in the terms of S. Now focusing on ES, let us simplify this in the terms of ES. What we will be having? We will be having Km into ES, Km 1 plus I by Ki into ES equals to, when I will multiply this with the substrate, then what we will be having? E naught into S naught minus Es into S. Now take this ES species toward this side. What we will be having? Km 1 plus I by Ki into Es plus Es into S equals to E naught into S. ES is common in both, so I will take this ES as a common, and after taking the common I will transfer the whole species toward the right hand side, and this will become E naught into S by Km, because I have taken this here and I am transferring this toward this side, so it will become Km into 1 plus I by Ki plus S, because here Es is also common, I have taken out from this, so it becomes S. Again, back to the Briggs-Haldane equation derivations. What we have seen there was a velocity was what? K2 into Es. So here we have the value of Es, and this value is this one. So again, replacing the value of Es here, so what we will be having? V naught equals to K2 into E naught into substrate by Km 1 plus I by Ki plus S. Okay, now again this one is equals to what? This one will be equals to the Vmax, so we got again the same equation as that of the Briggs-Haldane equation, as V naught is equals to Vmax into S divided by Km into 1 plus I by Ki, and it will be plus S. Just like that, what we have said that substrate is very large when we'll compare with respect to the enzyme. So here also inhibitor concentration will be very large when compared with the enzyme. So again we will take, instead of S and I, we will take it as a S naught, I naught and S naught, which is the total substrate concentration, total inhibitor concentration. So these were all about the variation of the kinetic. So what we have analyzed, when inhibitor is competitive, then there will be no change in the Vmax, but it will affecting directly the Km. So instead of expressing this whole term, I will replace this whole term with the alpha, that alpha is equals to 1 plus I naught by Ki. To analyze this graphically, let us plot this with the help of Lin-Weber-Burke plot. So when I will reverse this equation to find the Lin-Weber-Burke equation, what we will be having? We will be having, I am going to replace this whole term with the alpha, so it will be alpha factor of Km by Vmax by 1 by S, or the substrate concentration, plus 1 by Vmax. Now when we plot this against the plot as per the Lin-Weber-Burke plot, so what we will be having? We will be having this graph in absence of any inhibitor. So here also this point will be 1 by Vmax, this point will be minus 1 by Km, and this will give you 1 by V naught, and this will give you 1 by S naught value. But what will happen when inhibitor will be there? This will because here what we have seen that alpha factor is increasing. So here also in this case also what there will changes in the graph also. So this graph will also lead to the increase in the Km factor. So this graph, this point will shift toward the zero origin. So it will be shifted toward this side. So and when we'll compare both of this graph together, then what we will find that this is in absence of the inhibitor and in presence of inhibitor. So in presence of inhibitor as well as in absence of inhibitor, what we will able to see, this Vmax 1 by Vmax will remain same, Only the changes is what this is, this one is minus 1 by km, and this point is 1 by alpha km, or the factor which is been added to the km or multiplied to the km. So this will just going to increase the km value. Even if we will plot the graph on the Briggs-Haldane equation, which should be it will not affect the Vmax, but it will definitely affect the, in presence of inhibitor, it will affect the km. So in absence of of inhibitor, what we know, that half the value of Vmax, so this will be the half the value of Vmax, will give you the value of km when we will drop the parallel line toward the s-axis, which is the substrate concentration. Similarly, here also the V naught, or the V half of the Vmax, will be decreased and the km value will increase. So either in the Lin-Weber-Burke plot or in the Briggs-Haldane or the, as per the Michaelis-Menten graph, we will see that the competitive inhibitor directly affect the km value by the factor alphas, or we can say that km value will increase in the presence of inhibitor. It will not affect the Vmax. So these were all about the competitive inhibitors and the kinetics of the competitive inhibitor. In the next class, we will going to study about the uncompetitive inhibitor. In this, what happens, substrate as well as inhibitors has different binding sites, so they do not compete for the same site of binding. So don't forget to subscribe and share my channel. Till then, goodbye and have a nice day.